Welcome to the second lecture of our course on quantum mechanics. Now, last time in the first lecture, we previewed the course. We looked ahead at some of the strange features of quantum physics that we'll be learning from now to the end of the course. But before we do that, we must first describe something about classical physics, which can roughly be defined as the view of the physical world that prevailed before the year 1900. So we have to do a little history of physics today. And when we do that, I prefer to take the long view. So here's the big picture of the history of physics. Throughout the history of human thought, there have been essentially two ideas about the fundamental nature of the physical world. And lots of the history of physics has been a debate between these two ideas. And in a nutshell, those two ideas are either the world is made out of things or the world is made out of stuff. Okay, what do I mean? Things describes the idea that the basic constituents of nature are discrete, indivisible units. Discrete, indivisible units. You can have 1 unit or 2 units or 3 units. You can have 17 units, but you can't have 2.718 units. So when we ask a question about the quantity of things, we ask the question, how many? How many things do we have? In modern terminology, the things view is the digital view. You can have 1, you can have 2, but you can't have a whole continuous range of values. Then there's the stuff idea. The stuff idea says that the basic constituents of nature are smooth, continuous substances. You can have any amount of stuff. So when you ask a question about the quantity of stuff, you ask, how much do you have? In modern terminology, stuff represents an analog picture of the world. You can have any value of it. So let's bring it down to something real. Think about your dinner plate. Now, on your dinner plate, the English peas are thing-like, but the mashed potatoes are stuff-like. The peas come in discrete units. We can ask, how many peas do you have? I have 34 peas on my plate. But you really can't ask exactly how many mashed potatoes you have. You have to ask how much mashed potatoes you have. I have a half a cup of mashed potatoes. Now, the answer to the question whether a particular thing is thing-like or stuff-like, the answer is not always obvious. If you take the peas and you mash them up with your fork, then you get stuff. You get pea stuff, much like mashed potatoes. The fact that the peas came packaged in little fundamental units was not essential because inside the units was just some stuff. On the other hand, if you look at the mashed potatoes under a microscope, who's to say that the pile of mashed potatoes is not just an immense heap of tiny little mashed potato grains? It's like sand. Up close, you see that sand is composed of individual units, grains of sand. Sand is thing-like. But if you stand back and look at some sand dunes, they look smooth and continuous. So the question of whether nature is thing-like or stuff-like is going to be a little difficult to resolve. But that's the essential debate. Is nature essentially discrete, made of things, or is nature essentially continuous, made of stuff? Now, there was an early version of this debate among the Greek philosophers. On the one hand, you had the atomists, led by Democritus, who had an essentially thing-like view of the world. They said that everything in the universe was composed of tiny, indivisible units called atoms. And in between the atoms, there was empty space. Atoms and the void, that's the totality of the universe. And all phenomena are due to the motions and combinations of the atoms. That was the Greek atomist view of nature. Now, other philosophers, including the Greek philosopher Aristotle, held the opposite view. They favored the stuff-like view. They thought that the basic substances of the world are continuous and infinitely divisible, that there was no fundamental indivisible unit of matter. You could always divide it further. Now, why did they think this? Why were they unhappy with the atomist view? Well, interestingly, part of the problem was not the atoms themselves, but the void, the idea that there was empty space between the atoms. Aristotle didn't think that the notion of completely empty space made sense. He said that nature abhors a vacuum. And so because of that, he thought there had to be continuous substance to fill up all of space. Interestingly, this question about empty space will come up again later in the course, so watch for it. All right, you had the atomist view, nature's thing-like. You had the Aristotelian view that nature is stuff-like, continuous substance. And both ideas had merit. Both ideas could explain observations about the world. So resolving this question is going to be a little bit tricky. Ordinary everyday observations are not enough to resolve the question. All right, let's jump ahead a few centuries, about 20 centuries, to the 17th century. And there, the question we're considering is the basic nature of light. What is the basic nature of light? And once again, there are two prevailing ideas. On the one hand, you had Isaac Newton, the greatest physicist of his age, famous for his laws of motion and gravitation. And he also studied optics, and Isaac Newton came to believe that light is a stream of discrete corpuscles, he called them. Light is thing-like. There were little units of light. Light came in little units. And so the corpuscles of light traveled through space in straight lines unless something deflected them. And different colors of light corresponded to different types of corpuscles. There were red corpuscles, there were green corpuscles, there were blue corpuscles, and so on. And the intensity of light, the amount of light that you had, corresponded to the number of corpuscles that you had. So the question of the intensity of light basically boiled down to the question of how many corpuscles, how many thing-like units do you have in light? That's Newton's view. On the other hand, you had the view of Christian Huygens, the Dutch physicist, the second greatest physicist of the 17th century. And Huygens had the view that light is a continuous wave. And he took the analogy of sound. He thought light was a wave like sound waves. Light wasn't sound waves, but it was analogous to it. And waves are things that propagate through space and spread out throughout space. And so he thought that's the way light worked. And in his view, different colors of light correspond to different wave frequencies, just like the different musical notes correspond to different sound frequencies. And the intensity of light was the strength of the vibration in the wave. So that can be any continuous value. So Huygens said that the question of the intensity of the light was a how much question. How much wave do you have? Now we're going to talk about waves a good deal in this course, so let's take a few minutes to sort out a few facts and ideas about waves. Basically, there are three numerical quantities that describe a wave. First one is the wave speed, which we would write with the letter V. And this quantity answers the question, how fast do the oscillations in the wave propagate through space? And that's measured in meters per second. It's a speed. It's a speed. How fast is the wave going? Now, sound waves, for example, travel at about 340 meters per second, which is pretty far. 340 meters per second. That's the speed of sound. The second quantity about a wave is the wavelength, which is denoted by the Greek letter lambda. That's a lambda. How far is it between successive wave crests, successive disturbances? That's the question we're answering. So a sound wave is an oscillation in air pressure. And at any instant in time, there's a certain distance between one region of high pressure and the next region of high pressure, and that distance in space is the wavelength. It's measured in meters. It's a distance. So what's the length of a sound wave? Well, let's take a typical musical note. We'll take concert A. That's the A above middle C. It's the A that the violin plays when everybody's tuning up. And concert A has a wavelength of about 3/4 of a meter. All right? That's the distance between successive regions of high pressure. Finally, the third quantity, frequency, which is we denote with the letter F. And frequency answers the question, how rapidly do the oscillations reach a particular point in space? For example, how rapidly do the oscillations in air pressure reach my ear? That's the frequency. And with sound wave, that determines the musical note that I would hear. And it's measured, frequency is measured in the number of waves, or the number of cycles, per second. A typical musical note, concert A, has a frequency of 440 cycles per second. Now these three quantities, wave speed, wavelength, and frequency, are connected by what we might call the wave equation, which says that the wave speed, v, is equal to the wavelength times the frequency, lambda times f. It's a mathematical relationship between wave characteristics. And it's a very convenient relation. It means that if you know any two of the quantities, you can figure out the third. It means that for a given wave speed, a higher frequency means a shorter wave, because the product of frequency and wavelength has to equal the wave speed. A lower frequency means a longer wave, because the product of frequency and wavelength is the wave speed. Okay, let's get back to our main story. The question is nature discrete, thing-like, or continuous, stuff-like? And the Greeks had two views of matter. The atomists thought that matter was thing-like. The Aristotelians thought it was stuff-like. In the 17th century, Newton thought light was made of discrete things, corpuscles. Huygens thought it was made of waves. It was a wave phenomenon analogous to sound. It would be stuff-like. Now comes a really remarkable period in the history of science, the 19th century. And in the 19th century, physicists arrived at a very successful synthesis of these two ideas, a way of putting these two ideas together. They said that, well, whether nature is discrete or continuous depends on what part of nature you're asking about. In the 19th century, scientists came to believe that matter is basically discrete. Matter is thing-like, while light is composed of continuous waves. Light is stuff-like. Okay, let's take these two ideas one by one. On the one hand, in the 19th century, they came to believe that matter was made of atoms. They used the old Greek word. Why did they believe that? Well, it started right at the beginning of the 19th century with the English chemist John Dalton. And Dalton showed how the rules of chemical composition, the rules about what substances could be combined with what and in what proportions they could be combined, could all be explained by supposing that the substances were made of atoms. The idea is that each element is composed of one type of atom. There's a type of atom for hydrogen, there's a type of atom for carbon, there's a type of atom for oxygen, and so on. And that atoms of different elements have different weights. And the atoms combine to form clusters of atoms called molecules. And for example, water, as Dalton showed, water is composed of two hydrogen atoms and one oxygen atom composing a molecule of water. Now, let's suppose that a hydrogen atom has a mass of 1 unit, whatever the mass unit for atoms is, 1 unit, and there are two of those. Oxygen, it turns out, an oxygen atom has a mass of 16 units. So 2 hydrogens and 1 oxygen means that the hydrogen and oxygen must be combined in the ratio of 1 to 8 in mass. And indeed, that's exactly the recipe for water. And Dalton was able to explain all kinds of chemical recipes from this idea. So the idea of atoms became the fundamental idea of chemistry. Throughout the 19th century, they applied atoms to more and more ideas about what nature was made of. For example, they were able to explain the structure of crystals by the fact that atoms could be organized in regular arrangements. So if you see the facets of a crystal, the facets of a crystal have the shape they do because the atoms at the submicroscopic scale are in a regular arrangement in space. And so on. I could go on for some time telling you about all the wonderful things that the atomic idea gave to chemistry. Well, a few decades later, the physicists began to pick up this idea and to use the idea of atoms, the idea that matter is composed of little discrete pieces, to explain more and more things about the world. And I want to mention two physicists in particular, James Clerk Maxwell, the great Scottish theoretical physicist, and Ludwig Boltzmann, who was from Austria. And those two, among others, were able to show that a gas and the properties of a gas can be explained if you assume that the gas is composed of atoms. If you assume that the gas is composed of atoms, you can understand the gas's temperature, its pressure, its density, its viscosity, all the properties of the gas in terms of the properties of the atoms. The gas is a swarm of tiny particles, the particles moving and colliding according to Newton's laws of motion, which of course had been known for a couple of hundred years by this time. And the gas seems continuous because the atoms are very, very small. They're really, really tiny. And so even a small volume of air contains immense numbers of atoms. The most important insight, though, is their insight that heat energy is really just the random motion of the atoms, the random motion of the particles composing the gas. And that was a tremendous insight, because before this time, there were two ideas. There was motion, which was the purview of the science of mechanics, and there was the subject of heat, which was the purview of the new science of thermodynamics. And the two subjects didn't have anything to do with each other. But when they realized that heat was really just the energy of microscopic atomic motion, that meant that they were unifying two branches of physics. They unified the study of heat, thermodynamics, with the study of motion, mechanics. One subject instead of two. And that unification is a tremendous triumph of 19th century physics. Really a great advance in human thought. Okay, what's the other half of the 19th century synthesis? It's the idea that light is made of waves. Well, how do we know that light is made of waves? Well, we know because of Thomas Young. Thomas Young, remarkable English scholar. He was a physicist and many other things. He developed the theory of elasticity. He helped to decipher the Egyptian hieroglyphics on the Rosetta Stone. And in 1801, Young did a crucial experiment, one of the most important in the history of science, showing that light is a wave. And he also measured the wavelength of light and found that the wavelength of light is actually very short. It's less than 1/1,000,000th of a meter. Now, this is such an important experiment in the history of physics that we've arranged to actually do the experiment right here for you as a demonstration. It's actually not very difficult. So here's the basic setup for what's called Young's two-slit experiment. First, we have a light source. Here's our light source. We use a laser. There's no reason to use a laser particularly. You need a light source that only produces one color of light. In the Huygens view, that would mean one wavelength of light. And lasers are just very convenient these days. Young, of course, used some other light source. So here's our laser. And we're going to shine the light at a barrier here. And this barrier has a pair of very narrow vertical slits. The slits are very close together. They're parallel, and they're in the vertical direction. And they're very thin. They're tiny cuts in a piece of foil. So we're going to shine the light through these two slits, and then the light that passes through those two slits will go over here, and will be projected on this screen where we can see it. And I've tilted the screen a little bit so that you can see it more easily. Now, what do we observe? Well, when we shine light through one slit, we see a little smear of light on the screen. But what happens when we shine the light through two slits? Okay. There it is. When we shine the light through two slits, we see a pattern of light and dark bands. It's not just a continuous, smooth smear of light across the middle. It's an alternation between a light spot and a dark spot, and a light spot and a dark spot. Those light and dark bands, they go from side to side. That is to say, the smear of light is from side to side, and the bands alternate along that. Those light and dark bands are sometimes called fringes, interference fringes, because that's what's going on. What's going on is interference. What's interference? Well, light waves are emerging from each of the two slits. And so the light waves from each of the two slits propagate through space, and they combine at the screen. And what we see at the screen is the total light from both slits. Now, at the bright bands, the places where the pattern is very bright, that's a place where the waves from the two slits arrive in unison. They are oscillating together at that point. And so that means that the two waves add together and form a bigger wave, a more intense wave, and you get a bright light because, of course, wave intensity, the intensity of light has to do with how much the wave is oscillating there. So you get what's called constructive interference. Two waves that add up together to form a bigger wave. Two beams of light that add together to form a brighter light. What's happening at the dark bands, though, is kind of funny. You see, at the dark bands, then the two waves are arriving exactly out of sync. And so when the waves add up together to form a total wave, they actually cancel each other out. And there's no wave at all. There's no light at all there. And this is called destructive interference. And it's very strange. So to really prove what I'm telling you, we're actually going to do the experiment one step further. I'm going to very carefully cover up one of the slits. This is actually tricky because the slits are quite close together. They're only 1/4 of a millimeter apart. And so I'm going to take this index card. I'm going to very carefully slide it over. I'm going to cover one of the slits, and we'll see what happens to the light pattern when I do that. Okay, so I move it over very carefully here. I cover one slit, and I've covered them both. Now, there we go. One slit. It's dimmer, of course, because I've covered up part of the light, but also you notice there are no light and dark bands. So, two slits, one slit. Two slits, one slit. Because there are no light and dark bands when I cover up one slit, that means that when I cover up one of the slits, there are places on the screen where the light actually gets brighter. The places where there was destructive interference now are receiving light because I've eliminated one of the contributions. It's possible to cover up part of the light source and actually increase the amount of light reaching certain points. That's destructive interference. Now, if light were a stream of corpuscles, nothing like this could happen. This wouldn't be remotely possible. So Newton's theory is right out the door. It can't explain this simple observation that Thomas Young made at the beginning of the 1800s. Light is a wave because it exhibits constructive and destructive interference. And the two-slit experiment proves it. Huygens was right. Okay, light's a wave. But what sort of wave? What's waving? Well, once again, later in the 19th century, more light was shed, so to speak. A character returns. James Clerk Maxwell is the one who figures it out. Maxwell shows that light is a traveling oscillation of electric and magnetic fields, an electromagnetic wave. Now, the details are fascinating, but they're unimportant for our purposes, so I'll just give you the key point. The theory of optics, the theory of light, now became unified with another branch of physics, the theory of electromagnetism. They were recognized to be two branches of exactly one theory. Optics and electromagnetism were the same thing. And that's another triumph for 19th century physics, a triumph of the unification of ideas. So this is the view from 1900. On the one hand, we found that matter is made of tiny atoms. Now, in 1900, nobody has seen an atom yet, but very few physicists have doubts that atoms exist. A few have doubts, but most people are pretty sure that atoms exist, even though they're not exactly sure exactly how big they are, but they know they're really small, and they can explain so many things by assuming that light, or that matter rather, is made of atoms. Chemical properties, physical properties, and so on. Now, by 1900, it was clear that the atoms were themselves made of smaller particles. By 1900, they discovered the electron, which is a little negatively charged piece of matter that's a constituent of atoms. But that doesn't change the basic idea that matter is made of tiny particles. The second part of the 19th century synthesis, the second part of the view of physics from 1900, is that light is a continuous electromagnetic wave. So, matter is thing-like, light is stuff-like, wavy stuff, but stuff-like, continuous. So, that's 1900. And in the year 1900, the eminent English physicist William Thomson, Lord Kelvin, as he's remembered, gave a lecture at the Royal Institution in London, a public lecture about sort of the state of physics. And he said, the 19th century synthesis explains a lot about the world. It's a tremendously powerful set of ideas about the world. It unifies some apparently different fields of science. This is a great triumph. It unifies thermodynamics, the science of heat, with mechanics, the science of motion. It unifies optics, the science of light, with electromagnetism. Now, Kelvin and others are at this time interested in going a little bit further, trying to understand the relation of light, optics, with heat, thermodynamics. We all know that there is some relation. Very hot objects emit light, so there's got to be some relationship. And if we could understand that relationship, that would be the capstone of the whole edifice of classical physics. And so that's Kelvin's ambition. But Kelvin says there are two dark clouds on the horizon of physics. There are two dark clouds that seem to show that maybe this is not going to be very easy. And in fact, Kelvin is brilliant. He's brilliant because these two dark clouds each turn out to be a hurricane. Each of them is going to blow through and knock down the edifice of classical physics. Let's talk about them one by one. The first one is the curious experiment by two American physicists, Michelson and Morley. And this experiment basically is asking the question, what is light? What are electric and magnetic fields? The conventional view in the 19th century was that electromagnetism and light were all about disturbances or displacements of something called the ether. The ether is the medium of electromagnetism. It is to light as air is to sound. It's the thing that conveys light from place to place. And it pervades all of the universe. The universe is full of ether. And we know it's there because light propagates through space. And so the Earth in its orbit passes through the ether. And that means that right here in this room, there should be a pretty stiff ether wind, several kilometers per second, blowing through the room. So Michelson and Morley did an extremely precise optical experiment to try to detect this. And they very convincingly and spectacularly failed to do so. They failed to detect the ether. And so Kelvin said, this is a dark cloud because maybe it means that our ideas about light are wrong. And indeed, it's the Michelson-Morley experiment that leads to the development by Albert Einstein of the special theory of relativity. But we're not talking about the special theory of relativity. We need to talk about the other dark cloud. The other dark cloud is the problem of thermal radiation. As I just mentioned, all warm objects give off electromagnetic radiation. They give off light of one wavelength or another, not necessarily light that we see with our eyes. So, for example, the light bulb. If I run an electric current through my filament, then it gets hot and I radiate electromagnetic radiation. Now, if we use classical physics to try to account for this, how bright the light is, what color it is, we get badly wrong answers. And so Kelvin said, this is a problem. We need to understand what's going on. This dark cloud is the puzzle that becomes the origin of quantum physics. The question of light emitted by a warm object, the light bulb. Next time, we're going to talk about how two revolutionary thinkers, Max Planck and Albert Einstein, turned classical physics on its head, introduced quantum ideas to explain, in part, the problem of the light bulb. That's the birth of quantum physics. That's next time, and I'll see you then.